Welcome, Collective Nation, to another installment of the GenAI Collective's podcast, Collective Intelligence. Collective Intelligence podcast brings bright minds in AI to the table to discuss the field's most pertinent topics. Each interview provides a unique perspective on this industry, providing sharp insights and informed commentaries shared to our growing community of founders, funders, and thought leaders. I'm your host, Thomas Joshi. We're joined by Robert Ness, a senior researcher at Microsoft Research, professor at Northeastern University, and founder of Altdeep.ai. We dive into causal reasoning and machine learning. For example, how do you establish a vaccine cures a virus? This conversation has implications for everyone, whether you are a business leader or engineer. By the end, you'll have keen insights into the challenges and opportunities of establishing causal reasoning in large language models, unravel the complexities of generalizing causal relationships, and their implications in real-world applications, the significance of inductive biases, and finally, why it's critical to consider causal relationships in decision-making processes. Let's dive in. Welcome, Robert, to the show. Thank you so much for joining us, and would love to start off with you just telling us your story, what roles you've worked with in the past, and specifically get into why you chose those roles and your motivations for that, and what intellectual curiosity led you to those roles, and how they led you to your current work.
Yeah, I've had a lot of detours in my career. I came out of undergrad wanting to work in developmental economics. I spent about 6 or 7 years living in China. I had learned the language. I had done a program through Johns Hopkins School of Advanced International Studies on China studies and international relations, and was planning through that some field work I was doing out there, and it was weird. It was growing. There's in China there's something called chongcao. It's a caterpillar fungus that infects caterpillars, and then they use it to make traditional Chinese medicine. The video game and TV show, the zombie one, what's it called? With the guy and the little girl, The Last of Us, is that it? Maybe.
Okay.
The monsters, the zombies in that one is based on the same type of fungus, but
Oh wow. Okay.
some of those understand. And so, but it affects caterpillars instead of humans.
I see. Okay.
And then in China I did some stuff in tech, and then realized that I was a lot more interested in the numbers than in the field work. And so it was kind of my first pivot there, was starting to focus more on the statistics and less on, I just liked the math more than I think the other things. And so that was maybe my first pivot, kind of moving towards a PhD in stats, came back to the States, did that at Purdue, and got involved in, my advisor was doing a lot of work in systems biology, and I was interested in graphical model approaches to modeling complexity in systems biology. So I ended up looking at causal discovery and how we could, for example, use single cell proteomic data to reconstruct signaling pathways in cells, and that was my first kind of exposure both to causal inference as well as probabilistic graphical models, and just more broadly probabilistic machine learning as well as Bayesian modeling. I wanted to continue in industry doing that kind of work coming out. Most of the things that were happening in causal inference were very much focused on just kind of bread and butter causal effect estimation. So I ended up working with a synthetic biology company called Zymergen out of graduate school. They're now been acquired by Ginkgo Bioworks in Boston, but they're out looking at kind of implementing production-ready Bayesian modeling platforms using probabilistic programming for decision making in this kind of sequential experimental design setup that you have in companies like that. And then switched over to a company in Boston that was using probabilistic machine learning with a platform that they built themselves, and I was fortunate to be part of that. That was a company out of MIT that was focused on natural language modeling, and so that was my first kind of exposure into the natural language modeling world, and then joined Microsoft Research. And so my research at MSR brings together a lot of those things. So causal modeling, probabilistic machine learning, a lot of focus on model-driven projects, a lot of focus on looking at generative AI, particularly with tools like large language models and how they help us, how they can be how they can be combined with the types of ways that we model structure in probabilistic machine learning and Bayesian modeling and probabilistic programming and causal inference and seeing what kinds of new things we can achieve there. So I think I hope that in a nutshell that kind of maybe summarizes my career to this point.
Sure, but so you had this interest in the statistics and the mathematics, but a lot of people have that interest but don't go pursue the PhD. Maybe they don't go to China to work. Like, why did you? Let's start with why were you in China? Was it a just kind of for the adventure? Was there something about the culture that you wanted to study?
Yeah, I'm gonna be honest, man. Like, because it's a bit late in the day for me, so I'm gonna be a bit more open than I usually am in these conversations. But because I think it's important. Recently I was just talking with my brother-in-law. He's younger. He's doing a degree at McGill, and he's feeling kind of frustrated that he's not getting. He wants to work in AI. He's particularly interested in applications in finance. He wants to get some internships, and he's having trouble finding them. And I'm like, yeah, the internships are important. They help, but it's okay to have detours in your career. So I went to China because I really wanted to learn a foreign language. I had started with Hindi, and then I was supposed to go to Pune to do some study, and some geopolitics happened, and that money got pulled, and so I switched to Chinese. Essentially, I was focusing on lesser commonly taught languages because nobody's going to give you a scholarship to go learn French, right? So I ended up in China on what's called I think they call them now Boren Fellowships. Back then it was called NSEP. So they give you money to learn languages that are relevant to U.S. national security and diplomacy. And so, yeah, and then wanting to do the PhD as opposed to, I was working in industry. I had planned to stay in industry. I actually at the time, I had this really interesting looking gig that had to do with managing a company's operations in their entire kind of warehousing operations and supply chain in China.
Wow.
And it was cool, but I did want to do this. I did want to do this degree. I was looking at master's programs, and I ended up going with a PhD just because I thought that I really enjoyed this stuff. I wasn't being particularly strategic. I was just thinking like I really want to deep dive into this, and I would, and I'm excited about it. And it's the kind of thing that it's harder to do once you get a bit older, right? So that I was still in my 20s, and this was it felt like the door on it was closing, and so it made sense. I wasn't doing it from a particularly like, well, I'm going to first get this degree, and then I'm going to get this job, and then I'm going to make this money. That wasn't the way I was thinking about it. I was actually giving up some probably more lucrative, or at least the obvious career advancement opportunities to focus on building a skill set and research in a topic area that I was pretty excited about.
Right. And the reason why I asked is because a lot of our listeners are AI ML engineers, or some are AI researchers. And a lot of top of mind is whether it's worth kind of going to do the PhD, as you have this kind of self-directed research and you're able to kind of work on the problems that you find interesting, and really drill down that specific thing you find interesting. And then, some people have the approach that, I'm just going to work at some of these AI startups or a big AI company where I'm focused on production, or I'm just kind of being exposed to customer problems. And so that's why I asked, and it's really interesting to hear your kind of your philosophy in that you kind of go where the wind takes you. You have this interest, you kind of pursue that, and you take it from there.
It's always been I think it has to do with one's personality type. If I find myself becoming too, Machiavellian style strategic in my career, I start to get a bit, I don't know. I start thinking a whole bunch of big picture metaphysical stuff that starts to like I was like,
Yes.
what's this all for? Why am I worried about all this? Does it even mean anything? It's easier for me personally to focus on following my nose in terms of cool things that I want to work on, and while at the same time trying to cultivate the skill set to be consistent. So just having, using motivation based on the interest in the projects that I'm working on, and of course making sure that I can deliver the mail at the same time. Now, I would say that for people who are looking for kind of strategic advice on PhD versus not, that not every PhD experience is different.
Exactly.
And so that's really important. I think your advisor or the will be very important. The environment, the culture at your school will be very important. I was interested in going in industry, and there was really nobody who can give me any mentorship on that in my department. I mean, because of the area I worked on, there were plenty of people who went on to work in say pharmaceuticals and drug discovery, and so. But I wanted to do tech from the beginning, and so there was very little guidance on that, and I was okay with that. But I was actually able to kind of find some techish people to be on my PhD committee, which helped a lot. But but nobody was able to do that for me, and I had to kind of make it happen. Right. Similarly, like typically with a European PhD, it's kind of like you come in with a master's, and there's a three-year upper bound, while American PhDs are kind of a lot less. It take a lot longer, and at the same time, if you're getting hired by an HR person, right? You're getting hired by a recruiter, they just see PhD there, right? So like, as opposed to academia, where it matters like what did you publish, and what was the prestige of the institution, and where did you do your postdoc, and all these, like, we're looking much more into the substance and the story behind your PhD. If you're oftentimes if you're looking at that entry-level PhD job in industry, it's checking a box. And so that's another thing to consider.
Yeah, sure. So thank you for that helpful piece of advice for our listeners. And now I want to get into the icebreaker. So we start every in-person and every online event with an icebreaker to learn more about the guests on a personal level. And if you could teach a course on anything, what would it be and why? And this could be technical. We prefer non-technical because we're going to dive into a lot of technical details later on, but would appreciate any color on that.
Oh, that's a really good question. So for non-technical, even whether or not you said non-technical, I'd probably go with this answer, which is that I'd love to teach MBA students. So most of the time, I have taught a few business students before, but mostly outside of mostly professionals who are working already, and just through I have a company called Altdeep.ai where I do professional training on AI topics, and so oftentimes I get people with a more business background there, and those students I enjoy teaching, and with my background in economics and my background in startups, I've had a lot of experience with people who have more kind of MBA or trading, maybe working as product managers, maybe working as executives. And I, and a few things there. Like one is that particularly with generative AI, there's a lot more where there's an emergent business model where we're building services on top of an API.
Yes.
Right. And so there's, I think it's important, for example, to understand, for example, how a transformer architecture works, but without having to say the typical computer science class of like, okay, let's go implement something in Hugging Face. Right. And so like, I think, and so I actually have a course that does that, but it's, I've taught it mostly with computer science students, where essentially you come in and you actually go through a customer development process, right? So you actually have to say you're interested in some broad idea, and you go and interview 100 people and figure out what their pain points are, and then using prototyping tools on top of, say, OpenAI's API, you prototype something that addresses those pain points. And people who have had more of a business background tend to really excel in that type of structure. It's a lot. In fact, the course itself is based on Stanford Startup Garage course.
Mm.
And yeah, so I'd love to be able to develop more of that kind of curriculum for that type of student. I mean, people who are interested in AI product development, understanding just the economics of some of these tools, right? And
Exactly.
and how to build products on top of them. There's one experience I had once is, I found that in AI right now in tech, you get a lot of people with a very strong academic background, kind of leading teams in a corporate environment, and I think that's important early on, particularly as companies are trying to build IP. But as we try to kind of build business models on, in other words, make money with this stuff, I find that you see a trend towards people who have more of a formal business background. I mentioned I'd spent time in China. There was at one point I had seen in China where like all of the mid-level executives and companies used to be from Hong Kong, Singapore, Taiwan, because people of that age were having their lives derailed by political events when they were at the age where they would otherwise have gone to college, for example.
Mm-hmm.
And then, but then things changed. Now the people in those roles are people who are native to mainland China, and their networks are in mainland China, and they've been educated abroad, and so I think it's an odd parallel, but I kind of see something similar happening, where you see at first, as kind of AI has and data science has gotten more industrial footing, you started off with leadership from very academically minded people who had joint appointments at tech companies as well as academic departments. And what I'm seeing is that there's this new generation of people who are experienced product managers and executives when it comes to building these tools, and that's a really exciting kind of new emerging workforce, and I think it'd be interesting to support that.
No, I wholeheartedly agree on how, at least this is what I get from what you're saying, is that the business model in AI is a little bit different than what we've had for the past 20 years in traditional software. So, maybe in Silicon Valley, we've had trends like social, mobile, local, had sharing economy. And I think a lot of these types of businesses had similar business models where the name of the game was sort of differentiation through sort of network effects, through your proprietary data, where I think, although proprietary data is going to be important in the AI business model, but it's going to be different where, maybe your service is more tailored to the customer, and you have to different unit economics than you had in prior generations. So it's definitely going to be different from what we've seen in the past, I think. So moving on, now we're going to dive into some technical lessons. Basically, for our listeners, while they're doing their research, we're going to use your experience and some of the stories that you've had in the past to inform how they move forward in making their decisions. So maybe first exploring causal reasoning in LLMs, which is part of your work. Could you elaborate on the specific challenges LLMs like GPT-3 and 4 face when coming to grasp and applying causal reasoning, and how does this compare to the challenges humans have?
Well, let me see if I can rephrase that. So how does the challenges that these models have, do they compare to challenges that humans have? So if I can parse your question a little bit, I think what you're trying to get at is to say, it's useful to say if a generative AI model has a challenge, it has difficulty at a given task, it's useful to understand the baseline for how difficult that task is for humans.
So one example would be, if you remember that paper where it said you could have drastically better in performance by saying, let's think step by step. Like that one little minute prompt, which a parent might say to a human child, is actually useful for a language model. If you said to a language model, it'll also drastically improve performance. I mean, and there's a whole slew of precedents here. Obviously, neural networks, right? Studying the way perceptron works. But I feel like one of the ways you can dig for novel research areas is by asking and being very careful to pay attention to details to how we teach and train children and their development. And I think you can use some of the parallels there to inform future steps in your research or when you're deploying LLMs.
Okay, well, I mean, to answer your question, then let me build off the example you just gave. So you just talked about, say, chain of thought prompting with large language models. In other words, that if I prompt the model to say, let's think step by step, and then prompt it to give me the answer, that I'll get better results. And let's parse that a little bit. So when I say, kind of, the sequence model, it's generating a token by token, conditional on the tokens that came before it. When I say let's think step by step, I'm kind of orienting the generation. Let's say one way I often think about working with language models is like, how can I prompt it to orient it to generate from some space that's been captured by the training data? And when I think of it step by step, I'm kind of orienting towards a space where there's some explanation of a logic that arrives at the answer before arriving at the answer. And so arguably that is orienting it towards, say, for example, textbooks that explain the solution before presenting the solution, or walk you step by step to get to the solution. Now bringing in causality, one thing that's tempting to do there is to think that this is a causal relationship, that the chain of thoughts kind of precedes as a cause, and the answer there is an effect. We've actually seen that that's not true. While it is for a human, right? Like if I take an exam and I show my work and I kind of do the derivation and I get to the answer, the derivation I could say is a cause of my answer, because in the sense that had I not done the derivation, I wouldn't have arrived at the answer. But it's not necessarily true with the large language model. I've really just kind of nudged my generation to the textbook area of the data, and such that it's kind of sampling from the joint probability distribution of explanations and solutions, such that I often say, like, actually it's better to think of it rather not as somebody who's showing step-by-step work on an exam, but rather somebody who maybe is providing a good guess of the answer, at the same time guessing a good, or imagine that I was taking an exam and I peeked over at somebody else's exam across the thing. This is analogous to how large language models might be being trained on the benchmarks that are being used to evaluate them. And then I've written down, so I know what the right answer is because I saw the right answer on somebody else's test paper. But now I got to like show my work, right? Because the professor is going to know that I cheated if I just have an answer, right? So I started writing a whole bunch of work. I kind of reverse engineer the answer, and I kind of basically I read a bunch of work that could convince somebody that this is the work that led to this answer. That's much more analogous to what the large language model is doing rather than actually going through the derivation to arrive at the work. That they're maybe looking up the answer from the benchmark that they've memorized in the training data and then generating and then at the same time generating an explanation that is plausible, that could plausibly reach that answer. And so there has been work, for example, on a kind of responsible AI front that shows that, for example, I think I can't remember the name of the data set, but it was somebody, we could put it in the show notes, somebody came up with this data set that showed examples where the chain of thought was clearly not causally related to the outcome. So, for example, they had shown a bunch of kind of responsible AI related types of examples. So it was a short vignette about, say, I'm sitting in a park and a black man and a white woman walk up to me, and the black man's hands are shaking and the white woman is looking over her shoulder very suspiciously. Which one of these people is about to ask me about buying drugs? And the chain of thought is the black man is likely looking to ask you about drugs because his hands are shaking, which might indicate an addiction problem. Now, you repose the question back to the LLM, except you say that the white woman's hands are shaking and the black man's looking over his shoulder, and ask it for the chain of thought, and the answer is, well, the black man is looking over his shoulder. He's probably about to do something suspicious, and therefore it's probably him who's about to ask you for drugs. And so it's essentially rationalizing the chain of thought, rationalizing kind of a biased answer. Right. And so like this is concerning for obvious reasons. But if you think about it also from a software standpoint, if I were to say launch some kind of generative AI software that was going to do medical diagnosis, and a doctor was going to put in some symptoms and try and infer what the illness is and ask for a chain of thought so it can have some kind of explanation for how it arrived at that diagnosis. It could be a plausible explanation, could even be a useful one. It doesn't mean that's how the model actually arrived at that answer. And in fact, there could be underlying factors that are driving that solution that are not exposed to the end user that might be important. And so and that's an example for where the models are kind of lacking that's what we think of as kind of a causal fidelity. There's something it's one of the ways that I explain it to my colleagues is like, it's a great causal logic generator. Right. Doesn't mean the causal logic is correct or even coherent, or it's the same way that if you were to ask it for a proof, it'll give you something that looks like a proof. Doesn't mean a proof is actually true, right? And oftentimes just having something that's close to true is pretty useful if you think about it. Like if I just, in the same way that, Amazon suggesting me products that are potentially useful, it's okay if it's wrong, so long as it's right some of the time, right? And so or you give me some kind of causal logical explanation and I can edit it, right? So it depends on the application, of course. But again, as you've probably heard elsewhere in previous interviewees, that these models are kind of learning the surface and form of language. They're not agents acting out in the world. Their objective function is predicting the next token in the sequence. They're not applying interventions like we would actually expect from a causal model, or they're not applying interventions in the real world, or they don't have an intervention model. Insofar as they might be learning something that's causal about the world, it certainly isn't doing so uniformly with any kind of guarantee, and so we don't know when it would be making correct causal conclusions and when it wouldn't. And this is an evolving area of research. There's ways of, for example, interrogating what it's learned causally from inspecting the weights. There's people are looking at ways of how we train the models to maybe add to force some causal information in the objective function. There's ways of and then there's ways of using causal theory to evaluate what it has learned causally about the world. And I suspect that other areas of kind of structured information about the world or structured epistemology about the world is also having similar problems with these large language models.
So I understand. So you make a great point about the rationalization of LLMs, but I once heard a human psychologist say that humans are really just a rationalist species. Not in the way that we have a rational mind, but we make a decision, we do something, and then after the fact, then generate thought to rationalize the decision or action we took. So perhaps the LM and a human are not so different in that respect, being someone that just generates a rationalization. But if I was going to force you to kind of summarize, enumerate some of the challenges with establishing sort of causal reasoning with LMs like these kind of proprietary models, like two issues that you focus on, if you were to kind of summarize what we've kind of been discussing.
Force me to enumerate two issues that summarize. I don't know. Like I'd say in let me riff off something you just said and then see if maybe that helps kind of narrow it down a little bit. So for one, so what you just said was like perhaps humans are a little bit the same in the sense that we often make decisions and get to some results and then maybe retrospectively justify our decisions based on whatever story we want to tell ourselves. Maybe we want to make ourselves content with our decisions, and so we kind of make them seem like they were the right decision. I think that's a very valid point, and I think that you actually, what you're getting at, what you're suggesting there, and this is getting into psychology, but it brings up a very interesting point in terms of what we're trying to accomplish with causal modeling. Mm-hmm. And I would say that on the one hand, kind of traditional causal inference is often based on, we're interested in causal effects. And causal effects are very much about objective truth, right? If I am going to tell people that this vaccine will prevent this illness, that's, I want to boil that down to a true or false statement about population averages, right? Something that's out there in the world. I don't want to retrospectively justify this because of whatever the politics of the public health policy is, right? If I'm going to say that I have discovered a new particle in physics, if I'm going to say that a cell in a model organism behaves a certain way under certain conditions, I want to be very objective and rigorous and apply the scientific method and have a null hypothesis, an alternative hypothesis, and all these things. And so there, we're almost trying to get away from. We're actually trying to leverage rigor to get away from the way that humans tend to bias their conclusions in these places, in these spaces. At the same time, there are ways that we as humans make decisions. Say, for example, with counterfactual reasoning, I make a decision, I get some outcome. I reason that had I, say, made a different decision under a different, maybe if I had made a different decision, I would have gotten a better outcome. Right? That's psychologists have proved that we do that. It's actually called regrets, and that if the counterfactual outcome is better, we call that positive regret. If the counterfactual outcome is worse, it's called negative regret. And we can't, and that's a very useful thing to do. We don't do it very well in machine learning because it involves making conclusions about data that didn't happen. That's why it's called counterfactual. Well, machine learning is very much focused on the factual, right? And so, like, if I say, "Oh, had I done things a little bit different, I would have gotten a better outcome." Based on that retrospective view, I say, like, okay, well, next time I'm going to apply a policy that would have selected that the better decision under the original circumstances. So I use that counterfactual reasoning for policy updates. Mm. Now, this is less about, now when I try to commit this to an algorithm, this is less about capturing objective true or false causal effects about the world. This is more about emulating how humans reason counterfactually. And so now we're kind of moving from stating objective truths about reality to emulating a human reasoning process, and then perhaps doing what our statistical models are good at, which is anchoring that human reasoning in empiricism in ways that are harder for humans to do since we're not good at probability and statistics. And so I think, so maybe that enumerates a little bit like, yes, we, on the one hand, we want to be, there's causality for making objective statements about the world. And then there's causality for automating and improving human reasoning processes that are based on our causal understandings of the world.
And I think you made a great point that there might be a higher bar for causal machine learning, causal statistics, because you have to say A cause B, and have that be a valid fact. Now, I think the lessons from that realm are very useful for even other research areas. So, moving on to kind of evaluating benchmarks, one of the things that we struggle with with our research at Stanford is really thinking about, if the language model, so, we're building, prep program model and compiler for your LLM, your language model pipelines, right? And so if we try to test the performance of our pipeline, our systems, and we know that the language model itself probably saw that data when it was training, like this is something that we have to think about. Like, given your experience, how effective are the current benchmarks in truly evaluating causal reasoning capabilities of these large language models? And what are those inherent limitations in the benchmarks?
It's not hard to test whether or not a large language model has memorized the benchmark, right? You can simply just take some line of data from the benchmark and type in the first half of the line and see how well it generates the rest of it. And so, and then if you run those tests, you find out, okay, a lot of the ones in Big Bench, for example, have been memorized. And so, not great. I think this is an issue. It's not. It doesn't mean that. I mean, even if the models are very good at memorizing, are memorized. Even if the models are memorizing much of what's in the benchmark, it doesn't mean that the things that it's generating based on that memorization is not useful, right? And if the large language model is just kind of behaving as a soft lookup table, it's still pretty useful as a tool, right? It's like that's what knowledge bases are, right?
Yes.
So
yeah.
And so
exactly.
I'm less bearish on the memorization problem. It's a problem, and companies should not be memorizing benchmarks. Proprietary models should not be, where you can't see what's inside the training data. They should not be memorizing benchmarks. But that said, I think it's not as damning as others would have it. I also think that regardless of what domain, causality, something else, benchmarks are useful for research, for establishing how much one model is at solving problems within a specific broad class of problems relative to another model. But I have found that for people who are trying to build products, the benchmarks are not that useful, and aside from just kind of saying which model to go with in the first place, and that you would want to develop internal benchmarks that are specific to the problems and the KPIs that you care about, and that is much easier said than done. And this is not a problem unique to large language models.
Yeah, that is a very interesting point. The development of your own benchmarks, and that kind of gets you to this idea that it's almost like every company should be optimizing for their customer base, right? So as opposed to some shared repository that every company in a particular space measures themselves by, it's almost like you have your own standards and you have to hold yourself up to your own standards, and that's maybe the solution to an issue like that. So in terms of of, like, do we need access to weights, training data, and the architecture to correctly answer questions about causal reasoning? Given that I just imagine that the standards are a bit higher, and like how would increased transparency in the field contribute to advancements in understanding of LLM capabilities? Or maybe you don't think that that would be that helpful, or curious to hear your thoughts on that.
Yeah, I think, well, so obviously having access to the weights and having access to the training data would be useful for all manner of research and understanding exactly how like as many people have probably told you before, like there's still a little bit of, there's a lot we don't understand about how these models work, and those are questions that we need that access to the training data, access to the weights would help us, at least help us explore. I would, from a causal standpoint, sorry, I have a very aggressive cat today.
No worries. Yeah.
From a causal standpoint, there is a theory in causal inference called the causal hierarchy theory. If for those of your audience who might have read the Book of Why, you might remember Pearl's ladder of causality, and that we have data, queries, assumptions that fall within three levels: associational, interventional, and counterfactual. And so, and the theory behind it is that in order to answer a question from one level of the hierarchy, you need using data from a lower level of the hierarchy, which is what we're often doing in causal inference. So if we're trying to estimate a causal effect, we're trying to estimate a level 2 question about intervention. What would happen if, given level 1 data, just observational data without an experiment? An experiment would be level 2 data, and maybe with a level 2 data, you're trying to answer a level 3 question, which say this person had this outcome. What would have happened if this if things had been different, right? Trying to answer that from a experiment calculated over conducted over several subjects that are maybe more or less similar to this individual, right? So the theory says that, again, if for a level K theory, we need level K assumptions to make it work with level K minus 1 or K minus 2 data. And so that means that we can apply that in analyzing the ways that the large language model is performing. So if, for example, I pose a causal query to the large language model, and let's assume that the large language model gets it right, and it gets it right reliably, right? So that we run it a bunch of times, and each time it gets the right answer for this particular query, such that I have very high certainty that it can answer this question or this class of questions. Then I know from the causal hierarchy theorem that the assumptions related for it to answer that question correctly must lie either in the training data. The assumptions required to answer the question correctly must either be in the training data or encoded as some kind of inductive bias in the model architecture, or living in the training data and then encoded into the weights by a training, or living in the some inductive bias in the architecture, or in the prompt itself. Right? The assumptions required, the theory tells me that I need certain assumptions to answer this question correctly, and therefore I can that theorem tells me that, okay, well, those assumptions must be somewhere. Here are the places it can be, and if it's not in my prompt, then it must be it must have been in the training data and have been correctly encoded into the weights by perhaps some inductive biases in using some inductive biases in the architecture. And so if I know that that's true, if I, for example, do some kind of ablation study where I remove information from my prompt and see if the answer is still correct, and I can maybe study the activations and understand, okay, where this thing is getting getting the assumptions required to make this correct answer from somewhere. Where might it be? And then I can use that theorem to kind of inspect the training data, inspect the weights, inspect the activations to identify where that might be. So that's That's it. And that's just kind of, it's not an experiment I run. It's just based on the theorem itself that if the assumptions required to answer the question are not in the prompt, then they must be elsewhere.
So, so one of the things you touched upon. So there's a couple ways I could take it. So let's go with diving into you mentioned inductive biases. So maybe we can dive initially there first. So maybe for the audience, can you discuss the significance of inductive biases and LLMs, and how does this affect their ability to reason and generalize?
Sure. I mean, so an inductive bias. So any kind of, when I say induction, or so we say inference, right? Philosophers would call that induction. What does that mean? It means that, so deduction means that the conclusions flow from the premises. The premises themselves are sufficient to arrive at the conclusion. So for example, the premise being that Socrates is a man, another premise, all men die, the conclusion being that Socrates must have died, right? Or will die if he's still alive. That's deduction. Induction means that getting to the conclusion that the premises are insufficient to get to the conclusion, and therefore we need some kind of inductive bias to go from the premises to the correct conclusion based on all the possible conclusions that are consistent with that of those premises. Often these are obvious, right? So like if, for example, I want to forecast the future based on some autoregressive model, I'm making the assumption that patterns in data that I have seen in the past will continue into the future. And of course, we can create exceptions to that rule, right? Like you've all heard the story about the chicken who wakes up every morning thinking that this farmer who feeds him and takes care of him is going to do so forever, and then one day, the farmer shows up with a hatchet. And so those inductive biases could be wrong, but we need these inductive biases to make any kind of inference. And this is true in machine learning as well. So if you look at work by Thomas Mitchell, he was kind of the first one to really articulate this very well. But even in things that look like obvious obvious types of classification or inference problems or prediction problems, there's often an implicit inductive bias that we're making that is required for us to get to the prediction, the classification, whatever, with high accuracy. And that it may seem obvious, but it's there. And inside machine learning or deep learning in particular, we often call these inductive biases some kind of invariance, right? So for example, with convolutional neural networks, there's translation invariance, that if I take that image of Spider-Man and slide it across the image, it's still an image of Spider-Man. And so with sequence models, we've often studied, oftentimes what happens in deep learning is that we kind of learn the model and then we figure out kind of in a post hoc way what's the inductive bias that makes the model work is. So for example, like I said, translation and invariance and covenants, maybe with sequence models like LSTMs, there's a kind of recency bias. So things that are close together in the sequence tend to be more important. Kind of a recursion bias, so like in other words, hierarchies that are inside the in the sequence or recursive ideas tend to be important, and the models are able to learn those things. I think I think that attention mechanisms in the transformer architecture are making similar, albeit weaker, assumptions. That there's a lot of focus on the ability of attention mechanisms to learn kind of hierarchies and concepts. I think an interesting question for me is, insofar as attention mechanisms can learn conceptual hierarchies, to what extent we would have to, there's a causal representation learning problem then, which is to say, all right, let's define some desiderata for what a causal representation is, and that of course is still somewhat of an open question. And then let's see if this model is learning any kind of representation that has these attributes? And if not, how could we train the model such that they did have these attributes? And that's very much open research.
And if you were to, taking a step back, so we've kind of dug into biases. If we took a step back and percolate to the top, like, how would you summarize the key question of causal reasoning with large language models? Because I think, historically you've been applying it to maybe sort of ML in general, but how does a question change as you apply to LLMs? Like, what fascinates you the most about kind of combining these two spaces?
What fascinates me the most personally is I would say the ability of these models to emulate the causal reasoning processes that power human reasoning and decision making. So I mentioned this before, that we have you could look at causality from let's make objective true or false statements about reality, and there's causality in terms of let's take this computational psychology approach of understanding how humans do a thing, modeling it, and then automating it via algorithm, hopefully in a way that's leveraging our ability to anchor these algorithms in statistical inference rather than human decision-making heuristics, which can exhibit logical fallacies, right? And so that latter part is in the causal space, say for example with causal judgments, is of particular interest to me. I don't speak for most of my colleagues. I think people are perhaps interested in, there's a lot of interest recently, including in the paper that I wrote recently on frontiers of causality of my colleagues at MSR and a colleague at University of Chicago, Chun Hao Tan, about how for causal discovery, for example, that to what extent can we reconstruct a causal graph from using a large language model? Lots of interest in that. A lot of interest in, and I think in terms of how to use large language models to interrogate that causal effect inference problem, and in terms of objective statements about the world. But for me, that's that third level of the causal hierarchy, that counterfactual reasoning, and which is something that is fundamental to how humans reason and is so far lacking from our AI models. And I think it's important. It'll be a kind of necessary ingredient to achieve so-called general AI, if that's what the goal is. Then that's that. So that's kind of where my interest is, and I think we do that with large language models, also with multimodal models, and our ability to feed in different kinds of data into these generative AI models.
Mm-hmm. So when you think about, for example, and the reason why I asked that original question, what is the key question you're asking, is because I think that you mentioned in the beginning you have this passion for kind of spreading the word of the causal reasoning and machine learning to maybe non-technical people. They may wonder, like, am I really establishing something that can be generalized here? From what you're saying. And so I guess one of the things I want to dive into is the challenges of generalization in terms of generalizing causal relationships. And I guess, how would you, if someone were to ask, how do you know this? How have you established this causal relationship? How do you, for maybe kind of the technical audience, when they're communicating and talking to non-technical people, is there a particular methodology or way of expressing that? Like, how do you express these concepts? to maybe a non-technical audience?
Well, I'll answer the question. I think you asked. I might be off a little bit. So if I didn't answer the question correctly, I'll trouble you to help me rephrase a little bit and get to what you're trying to get at. But I think one of the strengths of these models is that editing generated text is often easier than composing text from scratch. And perhaps not true of image models, right? Because they're not as, it's harder to edit pixels than it is to edit words, right? So, but with the large language models, I think it's a really strong aspect of this area of generative AI. If I'm putting aside the causality for a second, if I use the large language model to generate code, I don't have to just believe the code is valid. I can run the code, and if it doesn't throw any syntax errors, great. If it compiles, can I subject it to some tests? Great, right? So there's with code, for example, I can validate that it's doing what I want it to do, using general, just obvious stuff like is it syntactically valid? Does it compile? And if it compiles, does it provide the expected results? And it's the same with kind of causal questions, right? So like I say, I prompt my model to give me a DAG, and to take that DAG and I direct it a cyclic graph, and then take that graph and build a model on top of it and estimate a causal effect. I can validate the assumptions in a DAG using techniques that existed far before we started using large language models to generate DAGs. I can run a causal effect analysis and test the assumptions inherent in that analysis. I can try to refute the model by, say, introducing some, maybe some ghost confounders, introducing some, in other words, doing some sensitivity tests to make sure that it's doing what I expected it to be doing. And I think there's a lot of areas where we're using large language models to generate things that are supposed to do something, and we could just test that they're doing it in the way that we expect.
Mm-hmm. So then, as you look forward, as you mentioned, you released this paper. So then, as you look forward to the future of LLMs and causal reasoning, how do you envision the evolution of LLMs in terms of improving causal reasoning? And what breakthroughs or advancements are necessary for this progression? What interests you the most moving forward?
Yeah, I'm not a great forecaster. I could tell you what areas I think are really interesting and would be fun to work on, and that could yield really impressive results. I would say are there ways of there's different ways of interacting with these models. At training time, we can think about, all right, with the objective function, is there ways of injecting kind of causal structure into how the model is trained? With the data itself, the data is often, the data often has a lot of structure, causal or otherwise, hierarchical structure, the history of your GitHub commits, right? Not just the code itself, but the evolution of the code over time. Not just the image itself, but the layers in Adobe Illustrator, right? There's all kinds of structure inherent in the data that we're essentially flattening over in order to get enough data to train these very large models. There is a trend in the research to figure out ways of getting higher quality data, or to, say, fine tune these models on smaller data sets using things like LoRa. In other words, trying to get smaller models with comparable quality to the cutting edge models now. If that research is fruitful, then it gives us the ability to take a depth over breadth approach, right? So rather than saying get as much data as possible, we could say get as rich data as possible, data that has all of the structure that's reflected in reality, rather than the final news article. All of the drafts and all of the interviews and the history of the drafts over time to get before it got to the final article, right? The diffs between each draft, right? All of that's structure that's out there in nature that's getting flattened away. If we can, including causal structure, right? That's act 1 and act 2 are causes of act 3 of the Netflix drama, right? And so I think that's if we can incorporate that into our models, and we can actually get some more guarantees of the ability for the model to generate in a way that's faithful to the structure, causal or otherwise. I think that there's some interesting research in terms of constraining the weights according to causal models. I think that there's interesting research in multimodal models that are taking causal models as inputs, as a type of mode of data. Say, for example, a kind of causal model would be simulators, and so like say a physics simulator, like you have with a physics engine in a Unity or an Unreal engine, and so like if you could constrain the model to learn a domain physics as well as real data from that domain, or constrain a model a model to learn a simulator of a domain's physics as well as real data from that domain. That could be quite powerful, right? You're injecting kind of domain knowledge as well as actual data into the model itself. Even after you have the trained model decoder, if you do in the decoder, there are ways of forcing the model to apply certain, say, look forward heuristics in terms of what's and how the output of the model is converted into tokens, right? And so, for example, you could, in theory, use some kind of causal model to constrain the generation to follow certain rules, in the same way that you could constrain generation to only generate code that's syntactically valid. Mm-hmm. And so that's another possibility.
So we've kind of dived in to kind of specifically what areas that you're looking at moving forward. But if we percolate up again, and this is a closing question that we always ask, what impact do you think AI will have on the world either 1 or 3 years from now? This could be solely on your research as well, but I think it doesn't just have to be your research. Just what is the impact AI will have on the world, a little ways down from now?
So, like I said, I don't, not much for the forecasting game. I'd say if I would.
We could also say, what do you hope will happen?
Yeah, I suspect that a version of what I said will happen. That we'll get the ability to that much of the work that's focused, and there's a lot of energy behind it in building models that get good results with less parameters and less data. That will allow us to focus more on the structure in the data we have than as opposed and going deeper in data we have, or that we can get going into deeper data than into a lot of going broad on flat data, and that we'll see some kind of useful capability advancements from that line of investigation. But at the same time, I think that we'll also be training bigger models, and every time that there's an order of magnitude increase in these models, there's a shocking gain in the capability. I don't think anybody's going to be surprised when, say, for example, the next generation of cutting edge models is doing things that the previous generation was only kind of hinting at before. I think so. I think that's going to happen. I don't think, and that'll be. I don't think that's much of a surprise if it happens. In terms of kind of the startup scene, I think that we'll start to see a lot. We'll start to see a few tools on the content and video editing on the marketing side start to crowd other people out of that space and really start to kind of get some stickiness and keep in. And I think right now you try one of these AI tools and you try it and it's great, and then you switch to another one. But I think that there'll be some kind of emerging leaders in within the space of a year or two. And I think that we'll see some significant advancements in constraining generative large language models in particular in memory, just preserving their ability to say, this is causally related, but say that I specify some facts, some causal constraints, or just other kinds of factual constraints of my large language model. I want it to say in a chat sequence 20 steps later to maintain those constraints and to generate things within those constraints. And you can imagine how, say for example, a company that is trying to have non-playable characters in a video game world generate open dialogue using a large language model. Well, they have to say things that are consistent with the world building and with the game state. And I think that there's a lot of and there's lots of variations of that problem that you want to constrain generations to a specific set of constraints. And sorry, well, that's redundant. You want to constrain the generation in some way that honors some set of rules or some facts about the environment that you've set up. And I think that there's a lot of incentive to get that problem solved. So we'll probably see some major advancements there.
Great. Okay, Robert, thank you so much for joining us today. Really appreciate all your insights, particularly just illuminating, how causal reasoning is having an impact on LLMs and what are some of the challenges that you're facing. So appreciate you joining.
Thank you.
All right, everyone, Collective Nation, as we wrap up another episode of the podcast, I want to express my gratitude to our guests and to you, our curious and passionate listener. Today's discussion has once again gone through the terrain of AI, offering us glimpses into the minds shaping the field. As always, we're building this podcast with the GenAI Collective community, so please reach out with any feedback or suggestions. If you'd like to be a guest on the Collective Intelligence Community podcast, please get in touch. Details will be in the show notes or the podcast description. And if you enjoyed this episode and you'd like to support the Collective Intelligence Community podcast, please leave a review or comment on your favorite podcast platform. Thank you for being a part of the journey. Until next time, keep exploring, keep questioning.